This is the historic old town of Godalming in Surrey. Here in the High Street, there are many fine buildings, some of them dating back as much as 3 centuries. The trouble with picturesque streets like this one is they're just too narrow to cope with modern traffic. There's inevitably congestion. This causes delays for the traffic, hazards for the pedestrians, and of course damage to the environment from pollution, noise and vibration. So Surrey County Council put forward a proposal to build a relief road, bypassing the centre of Godalming and diverting most of the traffic away from these narrow streets. In order to help them in the planning process, the council needed to know just how effective the scheme was likely to be. In order to predict the likely effect of the new road upon the traffic flow, they called in a team of consultants. And I went along to talk to Gareth Jones, who was the head of that team.
Well, as you've seen for yourself, Godalming, this is a map of the area, it does suffer from very high traffic flows down the High Street here. It's also a street with all the shops on it. Can't move the shops. Therefore, if you wanted to relieve a traffic conflict, we've got to move the vehicles. And there's been plans to build a relief road round the back of the High Street on the manner of this plan here. And we've been asked by Surrey County Council to develop a mathematical model to establish whatever traffic flows on this road. To do this in the mathematical model, we want 2 things. We want a representation of the network, which I'll come on to, but we also want to know the demand. Now, what we've done to establish that, we in fact hovered over Godalming in a helicopter, taking films every 6 seconds, and back in the office we can then trace the path of every car, vehicle, or what have you, coming in at the various entry or exit points. The network is similar to the plan here. In fact, we're upside down, but let me turn it around your way. Here we have the network defined as a series of, we call them nodes and links. I think you call them vertices and arcs, but it's essentially the same thing. These are the entry and exit points around the town, and we have to define every link in terms of its length, the speed down it, for subsequent model purposes. We number each node in order to do this. We certainly have some points where vehicles are starting or originating from within the town, but otherwise it's a fairly standard network. We do here see one-way systems, which is denoted by an arrow. Where there isn't, that's a 2-way flow. That we can then modify to put on the new proposed relief road. What we get from that is an indication, from the end of the model process, is an indication of the flows. This diagram shows the flows really. This bandwidth is proportional to the volumes of traffic flowing down the High Street in the morning peak period. There we see 757 vehicles going towards Guildford in this morning peak period. When we've put in the relief road, we see again that the traffic has moved away from the old High Street to the new relief road. If we compare those 2 diagrams, we can see that the 750-odd vehicles which were flowing down the old High Street have now been reassigned, rerouted to the relief road, 798 vehicles going in this direction and round. The effect of that, as we can see, is that we come from this high flow, 700 plus, in the High Street to only 791 vehicles, leaving the old High Street with just 91 vehicles, which is a very low level and there's no problem for pedestrian conflicts, etc. You could almost turn that into a pedestrian's precinct.
So you see, the key to understanding the traffic flow in a town like Godalming is to model it as a network flow problem. Now, we're going to be looking at this problem of flows in networks, and to help us fix our ideas, we shall suppose that we are in fact modelling a traffic flow in some road network. Now, our approach will be far less sophisticated than that used by Gareth Jones and his team, but hopefully we shall learn something of value about the true nature of modelling. Well, here's one sort of model. It's just a few bits of rope cut to scale and joined together to make a road map. And where the ropes are joined, we've labelled the road junctions. So suppose we wanted to go from this point S here to T over there. You can see several routes. We could go along here via A, we could go via D on the bottom, or there are several routes in the centre. Of these, which do you think is the shortest? This is in fact quite an important question. How do you find the shortest route through a network? Well, Euclid tells us that the shortest distance, in fact, is a straight line. The snag is we don't have any straight lines here, but that's where the rope comes in. Let us have a go at making some straight lines. Richard, would you like to give me a hand? If I take S, and you go over there and take hold of T, and if we pull, we should find... Now you see, we do have a straight line. And so, in fact, this route via B, along to C and to T, must therefore be the shortest distance, the shortest route between S and T. Well, that's a good party trick, but you don't want to go making rope models every time you want to find the shortest route. We need some alternative method, and obviously what we really need is a mathematical model. Richard.
When we make a mathematical model, what we're doing is to pick out the important aspects of a system and to represent them in a mathematical way. And over here, I've used a digraph to model a system of one-way streets. The arrows on the graph show us the direction of traffic flow, and I've used these numbers in circles to give us the length of each street, so that I haven't had to make the digraph a scale map. Now, in this example, there are lots of ways of getting from S to T, and my problem is to find, again, the shortest one. We could look at all the possible routes, but in a large network, that would give us just too many to look at, and we couldn't be sure we hadn't overlooked one. So what we need is a systematic step-by-step procedure, in other words, an algorithm. And these rings are going to help me to describe one. The algorithm itself you'll be meeting in Unit 5, so we won't worry too much about the details for now. I'll just go through the bare essentials with this example. And I'm going to use these rings to give me the distances of each vertex of the network from the starting point S. Now, the algorithm depends on the fact that if I'm on the shortest path, somewhere in the middle of the network, I must have got to any intermediate point by the shortest path from S to that intermediate point. So we start by exploring the 4 paths from S. And we can see that A is a distance 7 by the direct route, so I'll put a square for A at 7. B, similarly, is a distance 4, C a distance 9, and D also a distance 7. Now, if we look at the innermost one of the black squares I've put up, this is the one at B, we can deduce that the shortest path from S to B is by this direct route, simply because any other path would have to be a 2-stage one, of which the first stage is one of these 3 longer routes. So I'll note that we've already found the shortest path from S to B by changing B's square from black to white. Now we go back and repeat the process. We explore the paths from the white square at B. There are 2 of these, one up to A at a distance 1, so we'll place a square for A at 5, one further, and one down to C at a distance 3, we'll place a square for C at 5, 6, 7. And again, we look for the innermost of the black squares, and that's now this one at A, and we deduce that the shortest route from S to A is by this route, because any other would be a 3-stage route, of which the first 2 stages would be longer. So we'll note that by changing the black square for A to a white one. And incidentally, we now don't need this square for A, because we've got a shorter route than the one that has a distance 7. And we're glad we didn't waste any time on paths via that longer route. Now we explore the paths from our new white square at A. There's only one down to T, a distance 6. 6 and 5 make 11. There's our square for T. We look now for the innermost black square. We've got 2 at C and D, so we can just choose one of them, and I'll take the one at D to change to white. And we explore the paths now from our white square at D. 2 of those, one up to C at a distance 1, so that's a square for C at 8, and one up to T at a distance 4, so that's a square for T at 7, 8, 9, 10, 11, an alternative way of getting there in 11. Right, now again we look for the innermost black square. That's this one for C at 7, and again we don't need the squares for C by longer routes. And we'll explore the routes from this white square. There is only one. It's the route up to T at a distance 3, so I can place a square for T 3 further on from this 7. That's at 10. And that's the end of my algorithm. I've looked at all the routes to get to t, other than those that we know aren't the shortest. And the shortest one I've found is this distance of 10. So I can change that black square for a white one. And we remember that this shortest route to t came via C. The route to C with the distance 7 came via B. And the route to B with the distance 4 was direct from S. So we've got our shortest path. It's S, B, C, T. And incidentally, in finding it, we've also found the shortest distance from S to each of the vertices, where we've placed the white square. These numbers are often quite useful, and we call them potentials. And we can read these straight off the graph. A is 5, and B is 4, and C and D are 7, and T is 10. Well, now remember, you're going to meet that algorithm again in Unit 5, so don't worry about the details. But what I do want you to see is that there is an algorithm which will enable us systematically to find the shortest path through a network. And I also want to make a general point about modelling. By incorporating one aspect of the real system, that is distance, into our model, we've been able to use graph theory to solve a problem about the shortest path in the real system.
Following the shortest path is fine if you're on foot. But if you're driving, you need to be sure that not too many people have got the same idea. Narrow streets like these are all too prone to congestion. It doesn't need an accident or men digging up the street to cause a traffic jam. All it takes is a build-up of traffic beyond a certain level. Every road has a limit to its capacity. There's a maximum number of vehicles able to move freely down the road at any one time. And if more vehicles than that maximum attempt to use the road at once, the inevitable result is a snarl-up. So let's build this kind of capacity constraint into our model and see what happens. Well, the first thing we've got to do is to find some way of representing capacity in our model. Now, in the text, you've already seen a representation of capacity, and here it is. If you remember, this number 12 here means that the maximum flow along this arc is 12 units. You can think of it, if you like, as 12 vehicles per minute. Now, the way we're going to model capacity is to suppose that each arc can handle the flow perfectly well until it reaches capacity, and then suddenly no more. Well, obviously, this is not really very realistic in terms of traffic, but we'll stick with it because we want something fairly simple to give us a simple algorithm. So how do we begin? Well, we're assuming that all drivers will wish to follow the shortest route. But how many of them can actually manage to use this route? The route S, B, C, T. If you look at the capacities, we have 21, 18, and 18. So the smallest is 18. So clearly, no more than 18 vehicles per minute can use that route. So if the flow through the town were, in fact, just 18 vehicles per minute, we could imagine this situation. A flow of 18 along each arc on the shortest path. But BC and CT are now saturated. They can't carry any more traffic. So as far as any extra flow is concerned, BC and CT might just as well not exist. Also, the arc SB now has spare capacity for only another 3 vehicles per minute. That's the difference between 18, the existing flow, and 21, its maximum capacity. So again, for any extra flow, SB now has an effective capacity of only 3 vehicles per minute. So any traffic flow just over and above the flow of 18 per minute will effectively be confronted with this modified network. And if we assume that the drivers have been warned about the state of the town, it's reasonable to suppose that they'll then try for the shortest route through this network. Well, in fact, you can see that there are now 2 shortest routes. There's S, B, A, T, length 4 plus 1 plus 6, which is 11. And we also have S, DT, also of length 11. So presumably, extra traffic will spill into one or more likely both of these routes. Now, drivers are following the shortest route open to them because this keeps their costs down. And in fact, it's quite helpful to think of these numbers now as being costs rather than distances. So the situation we've now reached is one in which it's the cost that determines the route the traffic wants to take, and it's the capacity that says just how much traffic can actually use the route. If we keep an eye on both factors, we can begin to see how an increasing flow might distribute itself through the network. In fact, we're actually in a position we can pose a problem we should be able to solve. And the problem is this one. Suppose we have a fixed flow that we know wants to get from S to T. Say it's 37 cars a minute. How can that flow be achieved so it involves the minimum cost to the traffic involved? Well, we need another algorithm. Richard.
Now, you've already met one algorithm for dealing with flows. That was the maximum flow algorithm, which you met earlier in the unit on the cassette tape section. And you remember there we started off with a zero flow in a network, and then we had two steps. Step one was to find a flow augmenting path. And step two was essentially to send as much flow as possible down it. And we then repeated steps 1 and 2 until we had the maximum flow. Now I'm going to modify that algorithm to take account of cost. Remember, we can think of these numbers now as representing the cost instead of distance. And in place of step 1 in the maximum flow algorithm, which told us just to find any flow augmenting path, I'll substitute step 1 star, which will be not just to find any flow augmenting path, but to find the cheapest one. Now, if we're thinking of these numbers as the cost of travelling down a road, then the algorithm that we had earlier with the concentric rings, which gave us the shortest path, is now going to give us the cheapest path, which is just what we need for step 1 star. Okay, we've got an algorithm now that takes account of both cost and capacity. So let's see how it works with our network. We didn't go up to a maximum flow, we're just building a flow of 37, but the important thing is that we're going to get that flow at minimum cost. We begin by calculating the potentials at each vertex. Then we find the minimum cost route, that's SBCT. So that's the cheapest flow augmenting path, and we'll put as much flow down it as we can, that's 18. BC and CT are now both saturated, so we can't use them anymore. The total flow at this stage from S to T is 18. Now we go back to step 1 star again to look for the cheapest flow augmenting path in this network. We recalculate the potentials, and now we have two minimum cost paths, SBAT and SDT. Which do we choose? Well, we'll go for the one with the greater capacity. That's SDT. And we can send a flow of 16 along it. DT is now saturated, and so it can't be used anymore. And we note the total flow that's now 18 plus 16, that's 34. We're trying to find a flow of 37, so we've got to keep going. So back to step 1 star again, and we recalculate the potentials. But they haven't changed since last time, so the cheapest path is now SBAT. The flow along it is limited by SB, which only has spare capacity for another 3 units. So we send a flow of 3 units along SBAT. And SB is now saturated. Our total flow is now 18 plus 16 plus 3. That's the 37 we wanted. So that was our solution for a flow of 37, which was a convenient sized target flow as we reached it in just 3 steps without any difficulty. Now, if we wanted to do better than that and increase our target flow, we'd have to carry on with our algorithm, bearing in mind that we've now got 4 saturated arcs. But we'd run into a complication. We'd find that the cheapest flow augmenting path is now a rather complex one, S, D, C, B, A, T. And that includes this backward arc CB. Now, you have met backward arcs in the maximum flow algorithm, which was on the cassette section of the unit. And remember that a backward arc involves diverting flow. Here, we've diverting flow that was going down BC and sending some of it up BA instead. And if we went through the algorithm again, the maximum flow we can send down this path is limited by this arc BA. The spare capacity there is 16 minus 3. That's 13. So we can increase the flow by another 13 to a total of 50. And we'll then have a situation like this. And notice that because we've diverted flow from the backward arc CB, it's no longer saturated.
So we've been able to take the idea of distance or cost into our model, and we've amalgamated it with the ideas of flow and capacity you met in the text, and which has just shown us how flow will distribute itself through a network to achieve a minimum cost. Well, you may be wondering just what all this has got to do with the sort of traffic problem we saw right at the beginning of the program. Well, here's Gareth Jones again.
We certainly do use the shortest path algorithm for the model. We are certainly wanting to establish the demand by working out which is the shortest route through the town. It wouldn't be this fellow, it would be that fellow if we didn't have a bypass. So in that respect, it's very similar to your scheme. Your example, of course, used just one source and one sink, whereas in the real world, what we do have is a number. In this example, there are 7 points of entry and exit round the town. However, it's not a bad example because, in effect, the two major flows are certainly from here to there. All other flows, by comparison, are very small indeed. So it almost reverts to a one source, one sink example, in fact. The generalized cost, for instance, which is a fixed figure along this route. Unfortunately, we don't have a fixed figure along here for the generalized cost. The generalized cost is made up of two components, distance and time. Time is itself a function of the flow, as there is a relationship, so that it's not a fixed figure, but very much depending on the flows you've got. So that means you have to iterate around the model to get a balance. And again, you have a capacity assessment, but that's not a fixed figure. If we look at the relationships between speed and flow down the road, whilst the flow is fairly light, the speed remains unaltered. When it reaches a critical point, you might call it its capacity, it doesn't suddenly stop, such that you would have a graph like that, but it gradually starts to fall, so that as one minor correction in the real world, that capacity at a point such as this doesn't occur all of a sudden, it just reduces. So you can still get flows beyond what you might term is the practical capacity. In reality, there are other complications, other sort of delays we haven't talked about, but the whole situation is quite complex.
Well, of course, we never really thought that our naive approach would be able to cope with the real problems of traffic flow. But don't get the idea that this means that what we've been up to has been a waste of time. It's very necessary to begin by constructing a simple model to get a feel for the problem. So what we've done has been just a first step, but it is an essential one.
is